Greetings. This is Nate's rendition of homework assignment 10, problem 2, part 1, wide sense stationary process, WSS. WSS is a stochastic process like x of t, whose mean is eta, or the expected value, and it's constant, and its autocorrelation depends on tau, meaning that it's related to 2 points. In terms of points of interest that have come up during the research or the review, WSS only uses mean and autocorrelation. In practice, they are easier to get than second order density. Based on the mean and the autocorrelation function, we can do many things already. We do state estimation, parameter estimation, and prediction in the mean square sense. In communication applications, in most cases, we do not care too much on a specific value of the stochastic process. We place our concentration on the power of the, to be continued in the next section. This is a continuation of homework assignment 10, problem 2, part 1. Where we left off, we talked in terms of the power, with the emphasis being utilized with this particular process and how to refer to the signal. Okay, the correlation function R T1 T2 for the interval T1 equal to T2, which is that diagonal, i.e. R of T1 T1, is the average power of the signal at T1. Now, as I said, this is going to be a diagonal of the quadrant. We see that when input is WSS process, the output of a stable LTI system is also WSS. In terms of understandings, number 1, the Poisson increment, Poisson impulse, random telegraph signal processes are all WSS. The Poisson semi-random telegraph signal, random walk, and Wiener processes are not WSS. And to correct what I may have stated before, it's the Poisson increment that is WSS, not just the Poisson. So there's no conflict, just my misstatement. Number 3, if x of t is strict sense stationary and the expected value of xt exists, and xt is SSS, that is an error. It should be that if x of t is WSS, I think, yes. I will check on that and correct that one. All right, now on to number 4. X of t is WSS implies SSS, but it's not generally true, for WSS involves first order and second order moments. If x of t is normal and WSS, it implies that x of t is SSS, strict sense stationary. So the basic approach is, with strict sense stationary, And we will get into that, so I probably shouldn't really, well, I'll say it anyway. Fixed and stationary, we're dealing more with the impact of a time difference for basically linear time invariant systems. So really, when we deal with SSS, it's whether or not it's time invariant. It may or may not be a linear system. Where with WSS, it's not necessarily time invariant. And although one implies the other, meaning that if you're SSS, you necessarily are WSS, the reverse may not be true. So well, that's it. Thank you. Greetings. This is a continuation. This is homework assignment 10, problem 2, part 2. And here we are dealing with the independent increment process. By definition, what we're saying is if x of t1 minus x of t2 and x of t3 minus x of t4 are non-overlapping intervals, they are independent. Simply stated, and as reflected in the diagram. Discussion point. So far as we see, the Poisson random walk, Wiener, and Wiener are independent increment processes. It seems dependent increment property is somehow related to the Markov process. These independent increments are uncorrelated. In terms of perception, non-overlapping time intervals are deemed independent, constituting the independent increment process. The Markov processes, Poisson, semi-random telegraph signal, random walk, and Wiener, are comprised of, and we will continue this in the next section. Indeed, a continuation from section 2 for 3 words, independent increment processes. So the processes that were mentioned, the Markov family of processes, okay, the Poisson semi-random telegraph signal and the random walk and the Wiener process are all comprised of independent increment processes. Thank you. Greetings. This is assignment 10, problem 1, part 3, Poisson impulses. The first order properties, basically the probability masses, were not specified, and consequently I didn't do sufficient research to get them. The second order properties, the definition z of t, which apparently is another stochastic process, is equal to the first derivative of the stochastic process x of t. The mean n of t is equal to the expected value of z of t, which is lambda. The autocorrelation R of t1, t2 is lambda squared plus lambda delta t1 and t2. And the auto covariance is C T1 T2 equal to lambda delta T1 minus T2. Thank you. This is homework 10, problem 2, Part 4A, where we're dealing with the normal process, Gaussian. Definition is that x of t is normal if the random variables are jointly normal for any n, that is, if the density f of x of x1 through x to the n and t1 through t to the n is equal to 1 over the square root of 2 pi to the n times the square root of the determinant of c times e to the minus 1/2 x bar minus eta bar times transform times c inverse times x bar minus eta bar. And I think x bar, well, it's not necessarily the mu. Okay, that's it. Homework 10, problem 2, section 3, the Markov process. X of t is a Markov process if the past has no influence on the future when the present is known. Discussion. So far as we see that Poisson impulses, semi-random telegraph signal, random telegraph signal, random walk, and Wiener process are all Markov processes. In the real world, many processes have Markov properties. The binary transmission in the early homework is a discrete time, discrete state Markov process. In that case, we call it a Markov chain. Markov is exemplified in the graph or diagram to the right. I'll try to remember to mention that on all of them. I keep forgetting that. Although there's much more to the discussion points, one last thing, and it looks like it's a conditional situation, but apologetically, I cannot read. My vision doesn't allow me to read that, so all I can say is that there appears to be a scenario where we have a x of n, random variable, which is equal to x to the n, assuming x to the n plus 1 exists, and it's equal to x to the n minus 1. I guess I am reading it. My eyes adjusted. Then there's x to the n minus 2, etc. And that equals x to the n minus 2 through x 0 equals x of 0, sub 0. The probability that n is equal to x to the n, assuming or given x to the n minus 1 equals x to the n minus 1. So that exists and so much more, as was stated here. In terms of understanding, the Markov family of stochastic processes are not influenced by the past or future inputs or states, only their present values. Indeed, yes. 2, consequently, they can be classified as causal, static, linear systems. Thank you very much. This is homework 10, problem 2, part 4A. We're dealing with the normal process, Gaussian. Definition is that x of t is normal if the random variables are jointly normal for any n, that is, if the density f of x of x1 through x to the n and t1 through t to the n is equal to 1 over the square root of 2 pi to the n times the square root of the determinant of c times e to the minus 1/2 x bar minus eta bar times transform times c inverse times x bar minus eta bar. And I think x bar, well, it's not necessarily the mu. Okay, that's it. Greetings. This is homework assignment 10, problem 2, part 4, strict sense stationary process, SSS. And clearly stated here is if the statistics are not affected by a shift on the time axis, then the process is SSS. Discussion points. The SSS process requires f of x, the density function, x1, x2, x to the n, also by t1 to t1 to the n, to be equal to f of x, x1, x2, etc., but with t1 plus epsilon. Excuse me, t2 plus epsilon, t to the n plus epsilon. Although it's stated that this condition is very hard to meet, we will surmise that, certainly in our understandings, all linear time invariant systems are SSS. All SSS processes are WSS, but not all WSS processes are SSS. As long as shifts along the time axis do not impact the statistics, SSS exists. I might add additionally that must mean that the Poisson increments process is SSS. Okay, corresponding graph illustrates the essence of the strict sense stationary process. Thank you. Greetings. This is Nature Rendition, homework 10, problem 2, part 6, the white noise process. Defined as a stochastic process Vt if the expected value of V of t is zero mean, and the correlation of V, that's T1, T2, is equal to Q of T1 times delta of T1 minus T2. Discussion points of the fact that white noise for a Wiener process Wt, if we wish to discuss its derivative, Vt, it is equal to d of w over dt. We have the expected value of v of t times t equal to the first derivative of dw over dt, of the expected value of wt over dt, which is equal to 0. And our v then is still equal to t1, t2, but it is equal to alpha times delta t1 minus t2. The Wiener process, v of t, does have a derivative. We use v of t equal to wt over dt, just as a notation. When we need to do further discussions, instead of v of t, we use dwt. W of t is continuous with probability 1. It has a differential of wt. V of t is equal to dw of t over dt. It's Gaussian. Gaussian white noise with zero mean and an impulse autocorrelation function. We wish to define more general white noise with the zero mean and an impulse correlation function. Understandings. 1. While there are several approaches to addressing the white noise process, the focus in class will be on zero mean and an impulse autocorrelation function. The Wiener process of white noise is continuous with probability 1 and may be a preferred approach. Thank you. Okay, this is homework 10, problem 2, part 7. We're dealing with the mean ergodic process. Its definition, although somewhat complex, is x of t, the random variable x of t, is mean ergodic if the limit as big T approaches infinity of 1 over 2t, the integral minus t to t of the random variable x of t dt, and this being equal to the expected value of the random variable x of t. In the mean square sense, x of t is thought to be eta, but it is a constant. So consequently, WSS C, interesting, is the expected value of random variable x bar minus eta bar times random variable x bar minus eta bar transposed. Come close to being the correlation, autocorrelation. The theorem x of t, the random variable, is mean ergodic if and only if the limit as big T approaches infinity is 1 over 4t squared, one interval minus t to t, second interval minus t to t, of the autocovariance t1, t2, dt1, dt2 is equal to 0. Corollary. A WSS random variable x of t is mean ergodic if and only if the limit as big T approaches infinity is 1 over 2t, the integral from minus 2t to 2t, to big T, what appears to be the autocovariance of tau times the quantity 1 minus the absolute value of tau over 2 big T times d tau equals 0. Now, sufficient conditions exist also if the random variable t is WSS, which I find it hard to believe since the expected value is 0, and not to believe it occurs, and the integral from minus infinity to infinity is the absolute value of the autocovariance of tau, d tau is less than infinity, then the random variable x of t is mean ergodic. Now, x of t could be a process too. If x of t, now let's assume a random variable, is WSS and the limit as tau approaches infinity of the autocovariance of tau is equal to 0, then x of t is mean ergodic. Discussions. In the mean square sense, it's a kind of consistency. The remainder is kind of class obvious. Okay. This is a continuation of the mean ergodic process, and I wish to correct, but wish I could do it for everything, the notion that when I reference x of t, in many instances I've referred to it as a random variable. It is indeed a stochastic process, and there certainly is a significant difference there. I'll try to be much more accurate as I go forward. As we proceed, we wish to estimate the parameter values of stochastic processes. Lambda is the most important parameter, lambda equaling the expected value of the stochastic process divided by t. The Poisson process itself is kind of a summation, so we need not follow the general definition again. The limit as big T approaches infinity of 1 over 2t, the integral of minus t to t of the stochastic process x of t dt. We should estimate lambda by the fact that lambda t divided by t. So in this instance, we're looking at the stochastic process, probably expected value. We're saying that x of t equals lambda t, I would surmise. But let's follow the equation here. It is the limit as t approaches infinity of the expected value of the absolute value of the process xt over t minus lambda, the quantity squared. So the, what am I looking for, the term, in the mean sense, the value here, which is equal to the limit as t approaches infinity of lambda t over t squared, which is equal to lambda, the limit, as t approaches infinity of 1 over t, which is equal to 0. Therefore, the limit as t approaches infinity of the process x of t over t is equal to lambda. On to the next section. This is a continuation of the mean ergodic process, and I wish to correct, but wish I could do it for everything, the notion that when I reference x of t, in many instances I've referred to it as a random variable. It is indeed a stochastic process, and there certainly is a significant difference there. I'll try to be much more accurate as I go forward. As we proceed, we wish to estimate the parameter values of stochastic processes. Lambda is the most important parameter, lambda equaling the expected value of the stochastic process divided by t. The Poisson process itself is kind of a summation, so we need not follow the general definition again. The limit as big T approaches infinity of 1 over 2t, the integral of minus t to t of the stochastic process x of t dt. We should estimate lambda by the fact that lambda t divided by t. So in this instance, we're looking at the stochastic process, probably expected value. We're saying that x of t equals lambda t, I would surmise. But let's follow the equation here. It is the limit as t approaches infinity of the expected value of the absolute value of the process xt over t minus lambda, the quantity squared. So what am I looking for, the term? In the mean sense, the value here, which is equal to the limit as t approaches infinity of lambda t over t squared, which is equal to lambda, the limit, as t approaches infinity of 1 over t, which is equal to 0. Therefore, the limit as t approaches infinity of the process x of t over t is equal to lambda. On to the next section. Part of the mean ergodic process deals with their understandings. The mean square computation, taking the limit of the expected value squared to estimate the stochastic process, is primarily Poisson based. But it does not have a constant for its mean. 2. The WSS stochastic processes are assessed initially, but the mean square alternative may prevail in all cases. So regardless of whether the mean comes out to be constant or not. Okay, that's it. Thank you. This is homework assignment 10, problem 2, part 8, the martingale process. A stochastic process x of t is said to be a martingale if its expected value, assuming x of s is equal to the expected value x of t given x of s equal x1 quantity is equal to x1, where s is less than t. The conditional mean equals the condition. However, quite true for random walk and the Wiener processes. So the understanding is quite clearly what was stated, that the conditional mean equals the condition. And there are corresponding graphs. Okay, that's it.